Okay, I think we can start. So today we're very happy to have Liz Wildenhain from Berkeley, who will be telling us about islands in closed and open universes.
Thank you very much for the invitation. It's a real honor to get to speak. And I'm excited to share with you some work that Raphael Bousseau, my advisor, and I put out a couple months ago. It's entitled Islands in Closed and Open Universes. And I assume that many of you have at least heard of islands or may even be following it fairly closely, but I thought it would be useful to start with a bit of a reminder of what islands are and why they might be interesting. So as many of you probably know, there's this long-standing problem called the black hole information paradox, on which there was recently some interesting development. And this paradox appears when you consider an evaporating black hole. So one can imagine creating a black hole out of matter in a pure state. But according to Hawking's famous calculation, such a black hole is expected to evaporate, semi-classically, it should evaporate into Hawking radiation in a thermal state, regardless of how the black hole was formed. And this seems puzzling when you assume or expect that a black hole should follow the rules of quantum mechanics. And according to Hawking's calculation, it looks like you could have a black hole that starts in a pure state, but evaporates into a mixed state. And that looks like it violates unitarity, where pure states should evolve to pure states if we just follow the rules of quantum mechanics. And so this was a long-standing puzzle, and it's also often phrased in terms of the entropy of the Hawking radiation. It gives you a nice way to visualize or see the difference between these two expectations, one being unitary evaporation of the black hole and the other one being what Hawking calculated for the entropy of the radiation. So if you follow the entropy of the Hawking radiation and you assume Hawking's calculation just says you start with radiation, or you start with a black hole and then it evaporates into a thermal state. As more and more radiation comes out, it's more and more thermal radiation, and so the entropy of that radiation as a whole just increases. Eventually this would saturate if the black hole evaporates completely. But then if you instead expect the black hole to evaporate unitarily, you started with just radiation in a pure state, so the entropy of that radiation is 0. It collapses to a black hole. And then eventually, at the end of the day, all that's left is the radiation. And assuming unitary evaporation, that radiation should end up, again, having entropy of 0. So this lower curve here is called the Page curve. And that is what you expect if the black hole evaporates unitarily. And this top curve here is what Hawking calculated for the entropy of the radiation. And so the exciting recent development in which islands are significant, which I'll get to in a second, was showing in these papers here, showing that you could compute or find the Page curve of an evaporating black hole using what's called the quantum extremal surface prescription. And so the Page curve, again, is what you expect for unitary evaporation. And so these authors, instead of asking about the state at the end of the day, they just computed the entropy using the quantum extremal surface prescription, which I'll explain in a second. And the result was that the black hole's radiation followed the Page curve. So let me remind you what the quantum extremal surface prescription is. So the quantum extremal surface prescription, also, it's a generalization, I guess. The name that I'm using here is a generalization of a whole family of prescriptions that kind of evolved over time. So we have the RT prescription, HRT prescription. I'm just going to call all of those quantum extremal surface prescription, or sometimes I'll say RT prescription, but I mean the most general case. And this prescription is an ADS-CFT relationship. I'll remind you, ADS-CFT is a duality between a space-time, a quantum gravity, and asymptotically ADS space-time in D+1 dimensions, and a non-gravitational conformal field theory in D dimensions. And the quantum extremal surface prescription is a method for computing the entropy of a region in this boundary theory in terms of quantities in the bulk theory. So what the prescription tells you to do is, if you're interested in computing the entropy of a region on the boundary here, the circle is the boundary, the interior inside here is the bulk. If you're interested in computing the entropy on the boundary in some region R, you need to compute a bulk quantity, which is called the generalized entropy, which is defined for a surface in the bulk as the area of that surface plus the matter entropy enclosed by that surface. And in particular, for the quantum extremal surface prescription, one is told that you should compute the generalized entropy of a special surface, nicknamed the RT surface, or nicknamed the RT surface, which might look something like this, as kind of a schematic thing. But this particular surface is one that satisfies these three conditions here. So it needs to be homologous to the boundary region for which you're computing the entropy. It needs to be stationary in the generalized entropy. And then if you have multiple surfaces that satisfy those properties, you pick the one with the smallest generalized entropy. So that's the prescription. You start with a boundary region, find that satisfies these properties, and then you compute its generalized entropy. Is this cutting out? It's cutting out every so often. Is that a problem? I can move in. Okay. So this bulk region inside, which is enclosed by the RT surface, is called the entanglement wedge of the boundary region R. And it's kind of maybe a different perspective is to rephrase the quantum extremal surface prescription in terms of the entanglement wedge. If you like to think about it that way, then you could just say the entropy of this boundary region R is given by the generalized entropy of this entanglement wedge. And all of the conditions, so here's the generalized entropy of the entanglement wedge. And all of the conditions that I mentioned before, they're kind of included in this boundary of the entanglement wedge. So it still has to satisfy homology, stationarity, and minimality, but homology is for the boundary of the entanglement wedge. That's just like a different perspective if that is easier to think about it that way. It gets rid of that exterior of sigma, which means you have to define which is the inside and the outside. So maybe this is a nicer way to think about it. But either way, what these papers here computed was they applied this prescription to a setup in which they had a gravitating spacetime in which there's a black hole, and they coupled that to an auxiliary system in order to get a black hole to evaporate. And this auxiliary system is a non-gravitating system, and it's just collecting the radiation from the black hole. And they applied the quantum extremal surface prescription to this external reservoir, the auxiliary system that I'm calling it here. And they found, and that's supposed to be the entropy of the radiation that's coming out of the black hole. And they found that at the page time, or what we're calling the page time, there is a new quantum extremal surface, which becomes the dominant one. And by dominant, I mean, it's the one that is minimizing the generalized entropy. So it's the one you pick for the RT prescription. And it appears at the page time, and it's inside the black hole, and then it decreases because it's inside the black hole and the area of the black hole is decreasing. And this piece, is this disconnected piece, has been nicknamed an island or entanglement island. So it's a disconnected portion of the entanglement wedge, disconnected meaning disconnected from the boundary region or region that you're using the RT prescription to compute the entropy of. So that's what an island is. And it seems like it's important for understanding how to derive the page curve for this kind of setup. And you can also rephrase the RT prescription. I'm just saying this because you might have seen this in the literature. You can rephrase the RT prescription specialized to this kind of case where you have some auxiliary system which is non-gravitating, and you have some gravitating space-time, and you're trying to calculate the entropy of a region in this non-gravitating space-time. And this has been nicknamed the island rule. So it's just a specialization of the quantum extremal surface prescription to the case, though, the case where we have this non-gravitating space-time, which is where we're trying to compute the entropy. And again, it has to satisfy the equivalent conditions, the conditions in this case. So the entanglement wedge always ends up being, in this rephrasing of the RT prescription, it always ends up being the island, if there is one, so this could be empty, the island and the union of the island with the reference region for which you're computing the entropy. And then it has to be stationary and minimize the generalized entropy still. But something interesting about this calculation, which is partly, I guess, the inspiration for continuing to investigate it, is it seems like this quantum extremal surface prescription calculation was a semi-classical calculation. It still used Hawking's semi-classical bulk. And it also can be viewed as an application of the gravitational path integral in a saddle point approximation. So it looks like a semi-classical calculation that nonetheless captured an interesting feature of quantum gravity, namely the Page curve. And so it's natural that one might ask if we could use this this fact that it seems like semi-classical gravity might be more powerful than we thought to probe quantum gravity in cases where we don't really have a good handle on understanding quantum gravity. One of those cases is cosmology, and that is what I'll be talking about for the rest of the time. So this kind of question is what inspired this original paper here, Hartman and collaborators, and then Raphael and myself, to investigate what we could learn from the quantum extremal surface calculation, this island calculation, if we applied it to cosmological spaces, cosmological spacetimes. And the first question I guess you need to ask is, what kind of calculation can you do? How does this apply to a cosmological spacetime? And maybe that's not entirely clear. And so just kind of pick one that is tractable and see if it gives you something interesting. And that is, in that vein, the Hartman and collaborators paper kind of turned the usual question around, where instead of asking if we're given some reference region and we apply the quantum extremal surface prescription to it, what is the entanglement wedge? They turned that question around and asked, what if we have a cosmological spacetime and we look at a region in that spacetime? When is it possible for that region to be an island for some reference region? So instead of starting with the reference region and finding the entanglement wedge to see if there's an island, you start with a region and ask, could this be an island for something? And so this is the question that this original paper asked, where they chose the cosmological universe model to be a flat FRW universe. And I'll explain what that is in just a second. But a preview, as you may have guessed from the title of my talk, is that we then asked what would be the result of this, what would be the answer to this question in the case of a closed or open FRW universe. So you may be familiar with FRW universes, but let me remind you what they are. An FRW universe is a universe that is homogeneous and isotropic, or homogeneous means the same at every point, isotropic means the same in every direction. And the most general metric with those properties is the FRW metric, which takes this form here. There's a timepiece, of course, and then there's a spatial part where we've chosen coordinates such that this is the co-moving radius. So this is unitless, and then this A is the scale factor, which is the size of the universe at a particular time. And you have three choices for metrics that satisfy these properties. You can have a flat one, a closed, or an open one. And then this function changes form depending on which one of those you picked. So what you might want to imagine for an FRW universe is you have some spherically symmetrical universe, and then it has some dynamics, where the dynamics tells you how the size of the universe changes over time. And that time, or that's the size of the universe changing is captured inside this scale factor here. And the scale factor, the evolution of the scale factor is given by the Friedmann equation, which it takes a form that depends on what kind of content you put into your universe. So in our case, the content will include is radiation. So there's a contribution from radiation here, a cosmological constant, and curvature. And this gives you an equation for the derivative of the scale factor. So it tells you how the scale factor changes with time. And here's just the definitions of these constants. TC is more intuitively, it's a time scale on which the curvature starts to become the dominant contribution that determines the dynamics. Similarly, T lambda is the time when the cosmological constant starts to dominate. And then here, this rho is the energy density of the radiation. And again, we have three choices for the curvature. It can be flat, or it can be closed or open. So 0, +1, or -1, respectively. And then the Hartman and collaborators paper just looked at flat, and we'll look at closed and open. So given this question of how or when a region in a cosmological universe can be an island, the original paper here, Hartman and collaborators, derived some necessary conditions for that to be the case. Some necessary conditions for a region in a universe that's coupled to some auxiliary non-gravitating universe to be an island. And we likewise used these conditions, and we also derived another one that was relevant. It wasn't relevant for flat universes, but it is relevant for closed. And so the first, I'll show you what the four conditions are. The first one comes from the fact that if we have this is our cosmological universe here, this is the reference space-time. If we're going to have a region in here be an island, it must be favorable to add that region in the entanglement wedge. And by favorable, I mean it has to minimize the generalized entropy still. Otherwise, you wouldn't include that island. It just wouldn't be helpful in your goal of minimizing the generalized entropy. And you'll notice that adding an island to the entanglement wedge is expensive in terms of area. So if you remember, the generalized entropy was that area term plus the matter entropy enclosed by the entanglement wedge. If you add an island, you've now added that area term. So it must be worth it in that you still minimize the generalized entropy even when you add that island. And you can imagine how might that be possible? That will be possible if adding the island purifies something inside the reference system. So if you have a bunch of entanglement between this gravitating spacetime and the non-gravitating spacetime, adding the island could decrease the generalized entropy by decreasing the matter contribution by purifying something inside the reference system. And so from that, you can deduce that there should be a condition on the matter entropy of the island, which this original paper nicknamed the violation of the Bekenstein bound. So that's the first condition. The second condition comes from the requirement that the island together with the reference system need to be quantum extremal. Again, that was required for the quantum extremal surface prescription. And the quantum extremality is a statement about how the generalized entropy is changing with a shape deformation of the island. And so I guess I won't show you the whole derivation here, but if you combine this requirement with strong subadditivity and monotonicity of mutual information, you can show that this implies that the island needs to be quantum normal, where quantum normal is a statement about the quantum expansion of the region. A quantum expansion essentially just tells you how the generalized entropy is changing under a shape deformation. And so the island needs to be quantum normal, which means the expansion needs to be positive if you do a shape deformation outwards and negative if you do a shape deformation inwards. That's just the definition of quantum normal. So that's the second condition. Yes. Here?
Yeah, so here you said that for adding, if you want the islands, adding the island to be favorable, you want to have a lot of entanglement. And in the flat space case, that corresponds to a violation of the Bekenstein bound, right?
And also in closed and open.
Yeah, so how is this, like, how does it work in the ADS case? Why does it, yeah. So in the ADS, definitely something like this happens, right? Like, so.
Sorry, what?
In the ADS case, is there, why is there no violation of anything?
It works similarly. So if you imagine the original calculation where they had the evaporating black hole, which was ADS, and then the auxiliary system,
Yeah.
the interior is entangled with the radiation that's coming out. So it's still the same
Correct,
kind
but
of
we
setup.
wouldn't say it's a violation of a.
Oh, yeah, well, yeah, this is just the name of it. I guess it's just inspired by the fact that it kind of looks like Reconstructing. It's not, this is really just the name of this statement.
Okay.
Yeah. Okay. So, yes, so the second condition is that the island should be quantum normal. And then the third condition is pretty much just the same chain of logic, but applied to the complement of I. So by construction, we say that this universe, the cosmological universe and the reference universe are in a pure state. And if you assume that, then the union of this region outside of I and the region outside of whatever R is for which this is an island, that's also quantum extremal. And so by the same chain of logic, you get that G should also be quantum extremal, or quantum normal, sorry, where G is this complement of I. So that's the third condition. Those are the three conditions derived in this original paper. And there's another condition that applies only in the case where the universe is closed. So for a closed universe, you may notice that if you take a Cauchy slice of the entire universe, that slice, or the whole universe, always satisfies the first three conditions that I just listed. So the area term is 0, there's no boundary. And then it's automatically quantum normal because there's nothing to vary. And so that's always a valid option for islands with respect to those conditions. And so in order for a region inside the cosmological universe to be an island, it has to be a better choice than the whole universe. And again, by better, I mean it needs to minimize the generalized entropy. So that gives you a condition that, a condition on the matter entropy inside of G, just by analogous reasoning to the first condition. And so I've nicknamed this condition the better than everything condition. So the matter entropy inside G has to satisfy this inequality for a subset of a closed universe to be an island. So here are the four conditions again. In summary, we've got 1 and 4 are kind of complements of each other, and then 2 and 3 are complements of each other. So now that we've derived some condition that should hold if a region in a cosmological universe is an island, now you might ask, well, which cosmologies satisfy those conditions simultaneously? So which cosmologies can have islands? And in order to do that, in order to answer that question, you need a more concrete model. And so the model that the original paper used, the Hartman and collaborators model, and the one that we will use is to imagine that you have some non-gravitating space-time, and you have 2 copies of it. And we need to have some large amount of entanglement, because otherwise it's not going to be favorable to have islands. So we need some construction that has entanglement. And so it's a good question what might produce this entanglement, but just to start, we'll just assume that there is some construction with entanglement and we'll go from there. And so the construction that we choose is to take this non-gravitating space-time and double it and essentially construct the Thermofield double with 2 copies of these gravitating spacetimes. And then we want to have 2 copies of the non-gravitating spacetimes. We want to have a gravitating spacetime though, or cosmological spacetime. And so to get that, we'll then do a conformal transformation on this first one to add in the scale factor. And then this is the setup we want. So we have a gravitating spacetime that's a cosmology, then there's a non-gravitating spacetime, and then there's a bunch of entanglement between them. And
sorry, can I ask? These spacetimes are time dependent, and the Hamiltonian is not constant, right? I mean, it's so. How do you define the Thermofield state exactly?
Well, so the time dependence in the gravitating spacetime just comes in the scale factor. So we're just doing a conformal transformation where we just insert that scale factor. It's kind of like you computed the scale factor already, given whatever you decided to put inside the universe, and do So you know what that should be, and then you just do a conformal transformation. It's a kind of a brute force, but kind of my hand.
Okay, thanks.
Okay. Sorry. I need a larger head. Okay. So, and then the question will be, if we select a region in this spacetime, can it be an island? Can it satisfy those conditions? And so the results from the original paper, just the flat space case, are that the only case in which all of those conditions could be simultaneously satisfied was if the cosmological constant was negative. And then the islands that they found needed to exist near the turnaround time, so a place where A dot is 0, and they had to be large. So those are the results from this flat space case, just for comparison. But our question, as I've been saying, is what if there is non-zero spatial curvature? So now the next thing to do is to go through all of the different options. Oh, you have a question.
Just wanted to know what's the reason why you get islands only around the time symmetry point?
Yes. So you might guess that you only get them around the time symmetric point because it's hard to satisfy quantum extremality elsewhere because the area is changing away from the time symmetric point, the area of the universe. And so it seems like a natural place that you'd get them. You don't really know exactly what's happening with the entropy, so you might not want to be completely sure that it'll just be on time symmetric slices, but we will find that they are, in fact, just on the time symmetric slices or very close to the time symmetric slices. And yeah, so you'll see that is true in our analysis as well. But that's kind of the intuition for why those are. Yeah, it's a small window of order beta. So yes. So now the next question is, how would we, or we should go ahead and apply these conditions to a bunch of different cosmologies and see which ones we can have islands in. And the procedure is pretty similar for all of the cases. So I'll tell you what the general procedure is, and then I'll show you how it goes for a couple cases, and then I'll just report what the rest of the results are. So first, as you noted, it seems natural to guess that the islands would be on a time symmetric slice. So we're going to start out by restricting to time symmetric slices and later go back and check to make sure we didn't miss any. But to take like the intuition for this is what I just said. It seems like far away from the time symmetric slice, stationarity, it would be hard to achieve because the area is changing. And so we'll start with the restriction to time symmetric slices. In that case, the conditions, we can specialize them to time symmetric slices, and they take these forms in case you would like to track the details more. So these C subscripts mean co-moving quantities. And that really, this is really just saying that the scale factor has some expression or value at the time symmetric slice, which I'm calling A0, and sticking that into the conditions, and then rewriting this in terms of the co-moving quantities. That's all that's happened here. But in case you want to track the details more, these are the 4 conditions specialized to time symmetric slices. And then once we've done that, you can see A0 was in the expression, so we need to find A0, and that will depend on what we've put into our universe. So we always have radiation because we have this Thermofield double construction. That's just what we chose. And then we might have a cosmological constant of varying sizes, and then we'll have curvature of different signs.
Sorry, can I ask, how do you calculate the entropy of the radiation?
So we assume that it's just a thermal radiation. So it's just some thermal entropy density, and then find the volume.
Okay. And the number of fields that you have in your theory,
yeah, we just say their order unity, and it would change the numbers slightly, but
okay.
Yeah, we just simplify it by saying their order unity. So this, of course, can be found by just sticking A dot is 0 into the Friedmann equation, and then we'll get an expression for the scale factor at the turnaround time. And then the reason that we did this analysis before just sticking in the entire spacetime and just looking at the whole thing is it makes it easier to identify which regimes are the ones where we're not violating the semi-classical regime and where we find something interesting. So given this, we'll find that some of the regimes violate the semi-classical regime. By regime, I mean relative size of T lambda and TC. So then the next thing to do is just stick in the A0 that we found into the time symmetric slice version of the conditions. And the kind of island that we're picking, what we're picking as an island candidate is a spherically symmetrical island, which is centered at the origin and has a radius of chi. And so we stick that in, and we'll find for what chi can that region satisfy all of the conditions. And relevant conditions, I'm saying relevant conditions because that fourth condition only applies to closed universes. And in the case of closed universes, we'll separate looking at the whole slice and sets into two different cases. So then once we've done that, we've found we can find some cases in which the islands shouldn't, or the regions do in fact satisfy all the conditions. And if that's true, we can then check to see if there is an island, just because we can pretty straightforwardly. And then finally, we'll check the full space-time to make sure that we didn't miss any by our restriction to the time symmetric slices. And we'll find that we don't miss any, or we don't really miss any other than this narrow window around the time symmetric slice. So let's start with a simpler case, which is a lambda being 0 and a closed universe. So we already restricted to time symmetric slices by specializing the conditions to time symmetric slice versions. And so now we need to find the scale factor at the turnaround time. And you can do that, and you find that the scale factor is just TC. So now you can stick that into the time symmetric conditions, time symmetric slice version of the conditions for a spherical island candidate with radius chi. And like I said, for closed universes, we'll separate this into proper subsets and the whole universe. So first, let's choose proper subsets. And in that case, the first condition reduces to this expression. So you've got a ratio of the comoving volume to area. And the semi-classical regime gives us a restriction on this collection of constants here. And so you find that this will be satisfied if the island is nearly the whole Cauchy slice, so chi is large. And then with benefit of hindsight for having checked all the conditions, we'll skip 2 and 3 and we'll go to 4. And it's just the complementary condition for G. And it just ends up being the same, but with chi replaced to chi with chi minus pi. And so this one's only satisfied if G, which are G is the complement of I, if G is nearly the whole slice. And so that doesn't look too great because both the island and its complement have to be nearly the whole slice. And so these conflict with each other. And so we can not even do 2 and 3 because conditions 1 and 4 are mutually incompatible for proper subsets of closed universes on the time symmetric slice for this case. So then we can ask about the entire slice. And as I said at the beginning, while I was deriving the fourth condition, the whole slice is going to trivially satisfy all 3 of those conditions, and then the fourth condition isn't relevant here. And so it is a viable island candidate. And so since we found a case where there's a viable island candidate, we can check to see whether there is an island for some reference region, and choose the case where the entire slice is the island. And we have to, in order for us to actually have an island, adding that island candidate needs to be better than just not having an island at all. And so that will be the case if the reference region is more than half of this, the Cauchy slice of the reference spacetime. And then we can check the full spacetime to make sure we didn't miss any. And here I have plotted the, this is the co-moving radius and then conformal time. And these are the areas, the regions in which the different conditions are satisfied. I've put a cutoff here because you get some artifacts before the Planck time, but we cut those off. And you can see that there's no area or there's no region in which all 4 of the conditions are satisfied. And so we still don't have proper subsets that are islands. So now, I guess let me quickly summarize so the proper subsets for lambda being 0 and closed universe, they can never satisfy all the conditions, but the entire slice always does. And here's an example of an island, like I said. And then just for comparison, in the flat FRW case, there are no islands that are possible for this case where lambda is 0. So now I'll do closed universes with negative lambda. This will be the last example I do, and then I'll just tell you the rest of the results. So for negative lambda, we already restricted to time symmetric slices at first. We find A0, and we'll just look at this regime because if the cosmological constant starts to dominate very late, the opposite regime, or I guess just not early, then we end up with the same results as the previous case. So we'll just look at this regime here. And again, we'll separate into doing proper subsets and the whole universe separately. So in the case of proper subsets, you stick in your A0 and you find that the ratio of co-moving volume to area for the chi that you've chosen needs to exceed this collection of constants here. And then I do condition 1 and 4 together because they're complementary. So condition 4 ends up being the same, but with chi replaced to pi minus chi. And if you were to choose some numbers here, then you'd find that these 2 conditions are simultaneously satisfied for chi in this range, where this chi 1 is determined by whatever you've chosen for these constants. So it's satisfied for some range that's centered around chi is pi over 2. And then do the same thing with condition 2 and 3, stick in our A0, and you find that condition 2 and 3 are satisfied again for a range centered around pi over 2, but this chi has to be less than this one. This is on the time symmetric slice. And so the only relevant one, because this chi 2 is always less than chi 1, the only relevant one is actually here. And so the subset of this closed universe with negative cosmological constant is a viable island candidate in this range. Assuming again that we are in this parameter range. So let's just collapse all that and look at proper subset. That should actually be the whole universe, sorry. So, oh yeah, sorry. Step 3 for proper subset. So we're just checking to see if there is in fact an island for chi of this size. And indeed, there should be one in the case where the island and the reference system or the reference region are like the equivalent locations. So if you imagine just undoing the conformal transformation on here, the matching region in the reference spacetime is the region for which I is an island. So now let's look at the entire slice. And again, it trivially satisfies all of the conditions. And so it's a viable island candidate. And it will in fact be an island, again, just like before, it's if this region R is more than half of this reference spacetime, and we have to have condition 4 being violated, otherwise the proper subsets are better. And now we can check the full spacetime. Again, I have here, this is co-moving radius and then time. And you can see there is a region in which all of the conditions are simultaneously satisfied, and it's of width of order beta. And on the time symmetric slice, conditions 1 and 4 are more stringent, but that does change a little bit right there. But we see that we can still have proper subsets being islands, everything looks good, and we didn't miss any very far away. So in summary, the proper subsets can be an island now. And we can in fact have an island. And then the entire slice, like before, is still satisfying all of the conditions and is also a viable candidate. And then here's an example, like I said. Yes.
That if you have more than half of the bath, then you have an island. So my question is just, what's the topology of this bath? The sense more than half, so it's not
well,
a flat
I guess
bath.
half is measured for the co-moving coordinate. So it's like chi is pi over 2.
Okay, I see. Thank you.
Okay. And so, and again, for comparison, here's the flat space result. Islands were possible. They were large and near the turnaround time. So now let me just tell you the rest of the results. The procedure is basically the same. So if we have a closed universe with positive cosmological constant, we find that the proper subsets can't ever be islands on the time symmetric slice. And you check off the time symmetric slice, they're still not. And then the entire slice it's still a closed universe, it still always satisfies all the conditions. And then there's an example island, which is basically the same example that we've been saying. And then for comparison, again, flat, in this case, there was no islands were possible. And here's just a plot showing off the time symmetric slice. There are different solutions for the scale factor. So you can have a universe that expands, and that's this one here. You can also have a universe that bounces at some minimum, and so it does have a time symmetric slice here, but it still doesn't satisfy all the conditions simultaneously. And now the open universe cases, for a positive or zero cosmological constant, you find that there are no time symmetric slices, and so there are no islands on time symmetric slices because there are no time symmetric slices. And then if you check the whole universe, you still don't have any islands. So no islands in that case. And then for the open universes with a negative cosmological constant, you find that you do have viable island candidates on the time symmetric slice for some minimum chi, which is determined by these constants here. And but only in this regime. So T lambda much less than TC. Otherwise, condition 1 will conflict with the semiclassical regime. And again, you can find an example of an island with finding the matching region in the reference spacetime. And for comparison, the flat case, the islands were possible. Again, they needed to be large and near the turnaround time. And then you can check off the time symmetric slice, and you can see this region where all of the 3 conditions are satisfied, 4th condition not being relevant in this case. So here is a summary of all of those cases that we looked at. So we've got the 3 closed cases, the 3 open cases. The only one where we couldn't have any islands was open with either positive or zero cosmological constant. All of the closed cases, the whole universe could be an island. And also with a negative cosmological constant, we could have subsets being islands under certain conditions, like condition on chi and then conditions on those parameters. And then for open, we could have also subsets being islands, again, in a particular parameter regime. So that's the summary of the results. So now you might ask, well, what can we learn from this? And it's one of our messages here is just that curvature seems to be important to this question of whether islands are possible, even if there's just a small amount. So for example, the positive curvature guarantees that the entire universe is an island, regardless of anything else. So let's assume you have a closed universe, the whole universe is an island candidate. And that also allows for this new class of islands, which is with the subsets of the closed universes under certain conditions. You also notice that a small, but not arbitrarily small amount of negative curvature is going to eliminate the cosmological islands that were found in the flat space case. Another thing to observe is conditions 1 and 4 in the case where 4 was relevant, and condition 2 and 3 you compare which ones are more stringent, and condition 1 and 4 were always more stringent than 2 and 3. So observation, maybe that might be significant in some way. Just notice that is true. And another thing to notice is that in the closed universes, there was a maximum island size, because once you got past that, then you started violating condition 4, where the whole universe was a better choice. And so there's still some questions that I think are important to answer in order to really appreciate what the significance of these results are. Well, so first, one thing you could do is you could drop these homogeneity and isotropy assumptions and see, you could do similar analysis. And so I'm working on that with some collaborators from Israel. And you can also ask what would happen in the case where you have a more general FRW universe, maybe with a general fluid instead of just this radiation. And also cosmologies, islands as cosmologies, seems like maybe you could ask or say something about how islands appear or have significance in the multiverse. It's not immediately obvious how to do this. So this is an interesting question that I've been thinking about with some other collaborators from Berkeley. And another natural question is, you notice we've had this Thermofield double construction to introduce that large degree of entanglement. It was kind of just by hand, like we knew we needed to have a large degree of entanglement for the islands ever to be favorable. So we just stuck it in and to see what we would get, assuming that the conditions were favorable for forming islands. But it would be nice to have a dynamical explanation for what that entanglement might be. Because otherwise we can see that islands exist for favorable conditions, but you might ask, how can those favorable conditions be produced in the first place? And then perhaps most importantly, I would like to understand why it matters whether islands are possible in a particular universe. And with that question, I will thank you again for your attention and take any more questions.
Thank you. Are there any questions?
Yes.
So this is when you say that the entire universe is an island, so it sort of feels like it is connected in the sense that you were saying that an island is some region which is disconnected, but if everything is an island, this is probably just nomenclature, but
Well, it's not connected to the reference space-time. And the reference space, so when I say disconnected, I mean disconnected from the region for which you're computing the generalized, or which you're computing the entropy using RT. And that was a region in the reference space-time. And yeah, so I guess it's disconnected in that sense.
And then another question. So there is this correction to the, well, in the generalized entropy, you don't only have the area term, but the, well, correction from the quantum fields. I was just wondering, how do you compute that term?
Yeah, that's a good question. I guess, yeah, we just kind of assumed that it was small enough that it didn't apply. So let me think about that. I'll let you know.
Okay, thanks.
There were, yeah, questions back there.
Thank you. I was wondering, why do you need the reference space in the cases where you have a positive or zero cosmological constant? Because the motivation to add that auxiliary system comes from having a time-like boundary for ADS that doesn't allow radiation to exit the space-time. If you have a flat or positive cosmological constant, you don't have a time-like boundary to the space. So why do you need to add that reference space?
That's a good question. I'd probably just say, maybe this isn't particularly satisfying, but we're asking about the consequences of the island the quantum extremal surface prescription in the form of the island rule, and the statement of it was just, when do you have an island in the case where you have a reference system, and the reference system is the region for which you're computing the entropy. Also, you still do need the entanglement. And I guess make it most analogous with the other cases, just use the same construction for all of the cases as a way to introduce the entanglement required to make the islands favorable. Does that answer your question? Yes, yes.
Thank you. You can only get proper subsets that are islands when you actually need the reference state to allow.
Yes, that's a good observation.
Question here. In the case when you have an island, in the closed case, how do you get conclusions about the size of the radiation system? Because the candidate island should
Sorry,
be.
couldn't you, what about the signs?
How do you get conclusions about the radiation system? How big the size of the radiation system
How do you get
should be?
conclusions? Is that what you said?
Yeah, yeah. How do you get conclusions about that? Because the island should be only in the gravitating region.
How do you get conclusions?
At
In
some-
the case where you have a closed case, how do you get conclusions about the size of the island?
the radiation region, because you mentioned that you have an island when the size is bigger in sigma R.
Oh, like where the radiation is? Is that what
Yeah,
you're saying?
how do you know?
Oh, well, we just assume we have a thermal radiation density everywhere. It's a kind of, I guess, maybe simplified construction. You could ask where that would be produced. I guess that's this question here. What would be the source of the high degree of entanglement? Is that what you're asking though?
Yeah, I'm just asking because you have the conclusion that the radiation system should be bigger than the region have be bigger than size, half of the size of the radiation region. Something like
Oh, the reference system.
The reference
Is that what
system,
you
yeah.
mean?
that. Yeah, yeah.
I guess that's just the case where here, let me, maybe if I go back to, I don't know how helpful if you see the picture again. Might take a while to get to it. Oh, so something like this. You're asking about how do you get a conclusion about the size of the reference region?
Yep.
Okay. So I guess we need to purify enough of the, so we need to purify enough of the reference system. We assume that there's a thermal entropy density everywhere in both of these cases. And at some point, so you can look at the size of the area for a given chi versus like the volume of the area for a given chi, and then the entropy density will, that contribution will go with the area and the other one will go, or that contribution will go with the volume, and then the other contribution will go with the area. And so you can compare those and see when one of those becomes more significant. So, and that'll tell you when it starts becoming favorable to include the island. Does that answer your question?
Yep.
Okay.
So this is related to your first open question, the fact that,
Sorry, just bring it up again. Here?
So yeah, do you expect these results to be strongly dependent on the content of the cosmology? Because for example, it seems like the first condition should definitely depend also on that, like on the fact that you have radiation specifically. If you have, say, do you expect to have some kind of energy condition that the matter must satisfy in order to have islands, or do you think it's a pretty general feature?
Yeah, I think it's a pretty general feature. I don't think there's a real strong reason to expect this to be different. So it's more like this is a pretty simple generalization that we could do. Maybe we'll get something surprising, but we're not going in with this expectation that there would be something pretty different. I guess for the more general FRW, the question might be more really like if you get enough entropy. And so that's the question there. But other than that, it seems pretty similar. Is that a question? Okay.
Sorry, I also have a question about the non-homogeneous case. If we have a state where there is not a lot of entanglement between the two sides, so we have a small region of the reference system entangled with a small region of the cosmology, and otherwise the state is pure on the left side. Do you expect to have a small localized island around that region, or?
I guess we always find islands have to be relatively large, I think, because, well, I guess, yeah, I'm not sure how small you mean by small, but we always find that they have to be relatively large because otherwise
But what you did was for the Thermofield state. My question is about a different state where.
Oh, yeah. Well, so I guess the first thing we need to figure out is how to make the Thermofield double construction equivalent. That's kind of what we're working on. We're pretty early stage of this part. So yeah, that'll depend on how you're going to make how you're going to stick in the entanglement, I guess.
Okay.
So I'm not sure I have a good answer for that yet.
Okay, all right, thanks. Okay, if there are no further questions, let's thank Liz again for the very nice talk.